Here's an example of a problem from 2.2. In this example, you're given the graph of a polynomial and you're asked to come up with the rule for that polynomial. Now first thing, notice that I've asked for the polynomial of minimum degree. To determine that minimum degree, you have to think about turning points. You might remember reading in the textbook that a polynomial of degree n has at most n minus 1 less turning points. So for example, I've done a little tiny illustration here of a graph that you're familiar with. Y equals x squared, whose graph is a parabola, and it has one turning point. Now, this is a polynomial of degree 2, and it has one turning point. So if we want one turning point, the minimum degree is 1 greater. That would be 2. Now this graph has 1, 2, 3 turning points. Let me put this in a box off to its side so we don't get confused. This graph has 3 turning points. So the minimum degree is 1 greater, 4. Okay, so we know we're looking for a degree for polynomial. Now, another thing we can get from the graph, we see the zeros of the function on the graph. The zeros are -1, 1, and 3. Whenever you can see a 0 of the polynomial, then that automatically gives you a factor of the polynomial. For example, let's start with 3. If 3 is a 0 of the polynomial, then x minus 3 is a factor. Similarly, if 1 is a 0 of the polynomial, then x minus 1 is a factor. And you can probably guess the last one. If -1 is a 0, then x minus -1, or x plus 1, is a factor. Now a couple of things are missing here. First off, there could be any number in front of all these factors. We could have 200 times all of these factors, or -5 times all these factors, and still the zeros will be 3, 1, and -1. So if we're only looking at the zeros, there could be any coefficient out front. So we're just going to put a letter there just to stand for that leading coefficient. And this is the part that a lot of people forget when they're solving these problems. They forget about the leading coefficient. Okay, we'll come back to that, but there's one other piece missing. Let me rewrite this real quick before it just looks neater with the x plus 1 there. Now, take another look at this polynomial. This polynomial has degree 3. We have these 3 factors. If we multiplied all this out, our greatest power of x would be x cubed. Right now this thing has degree 3. If it has degree 3, it has at most 2 turning points, but we can see that this thing has 3 turning points. So we actually need degree 4, like we said in the very beginning of this problem. This is when you can think about the multiplicity of each of these zeros. Since the graph cuts through the x-axis at -1, we know that x minus -1 has odd multiplicity. Put a little multiplicity there. Okay. Since the graph cuts through the x-axis at 1, we know that this x minus 1 factor has odd multiplicity. Since the graph bounces off the x-axis at 3, it looks like a parabola at 3, we know that this has even multiplicity. So 3 is a 0 that needs to have even multiplicity. And the way we've written it, it's degree 1, that's odd multiplicity. Okay, well, so let's make it even. Let's just make it squared. Now, this polynomial has degree 4. You have an x squared here times x, so x cubed times x again, so x to the 4th. So now this polynomial has that minimum degree that we need. The one thing we have left to do is find that leading coefficient. And to find the leading coefficient, a, you should use the y-intercept. So, the y-intercept on this graph is -3. This actually gives us coordinates for the graph. We know that when x is 0, so when we substitute 0 into the function, we should get -3 for our y value. when x equals 0, y should be negative 3. So when we substitute 0 for the x here, we should get negative 3 for our output, for our y value. Okay, so let's actually put 0 in place of all these x's. So p of 0, let me see if I can reach. I'm going to slide this a little bit so I have room. Okay. If we substitute 0 for all of those x values, let's see, you have a times 0 minus 3 squared times 0 minus 1, substituting 0 here, times 0 plus 1. And we know that that should equal negative 3 for the y value. Now this is negative 3 squared, so this is a times 9 times 0 minus 1, negative 1, times 0 plus 1, 1. Should equal negative 3. So let's see, 9 times negative 1 times 1, so negative 9a equals negative 3. Divide both sides by negative 9. And we have a equals 1/3 when you simplify. That was the last piece of the puzzle. So now if we come all the way back up, circle this, come all the way back up to where we left with the polynomial there, we now know, let me see if I can write this off to the side here, that our polynomial is 1/3 times x minus 3 squared, just copying what I have here, 1/3 x minus 3 squared, x minus 1, x plus 1. And there's the polynomial we were looking for.